Solar cell. So in this we'll do the introduction, principle of operation, spectral response, homo-junction solar cells, heterojunction, therefore so cascaded heterojunction solar cells, material requirements, divided. As we all know, energy radiated from the sun is in the form of electromagnetic radiation which falls on Earth mainly in the spectral region UV to IR, that is 0.2 micrometers to 3 micrometers. The other radiations include radio waves are also present but with less intensity. Part of this radiation reaching the Earth from the Sun is scattered or absorbed by the Earth's atmosphere. Depending on the angle of incidence, the intensity of radiation varies between 500 to 1000 watts per meter square. Conversion of optical energy into electrical energy is known as photovoltaic effect. Solar cell is such a device in which solar energy is directly converted into electrical energy, and solar cell is an important photovoltaic device for obtaining energy from the sun. And the principle of operation is the photovoltaic energy conversion process may be expressed by the equivalent circuit shown in figure. An ideal diode is connected in parallel with a constant current source which represents the photovoltaic energy generated and with a load resistor. Consider a conventional solar cell exposed to solar radiation. Let the photon energy be greater than the band gap energy of the semiconductor material. Part of this energy equivalent to the band gap energy is contributed to the cell output and the remaining is converted into heat. In equivalent circuit, a current source is connected in parallel with the junction. The photo-generated current IL results from the excitation of excess carriers. The IV characteristics of the solar cell is represented by I is equal to ID minus IL, which is given by IS into exponential EV by KT minus 1 minus IL, where IS is the diode saturation current. In the dark, drift of thermally generated minority carriers across the junction constitute the reverse saturation current. At zero bias, this is balanced by a small flow of majority carriers in the opposite direction, resulting to zero net current. If the diffusion lengths of holes and electrons are given by L, H and Le, the lifetimes tau hole and tau H and tau E with the concentration per unit volume is given by P0 and Pn0. The reverse saturation current is given by equation, and A is the area of surface. The junction is illuminated by photon energy Hν, and which is greater than the energy gap. Additional electron hole pairs are created with a generation rate G per unit volume. Number of holes created per second is ALHG, and the number of electrons created per second is ALEG. So the total photon generated current is given, so IL. So the third equation, fourth equation you get, and we'll draw the characteristic curves, and the short circuit current is expressed in this way. So these are the equations you can derive easily. This is the current equation. This is the AH P0 E exponential plus the EVOC by KT minus 1, sixth equation, and from the sixth we will get the seventh equation. Simplifying on simplification you get 8, and we can find out the open circuit voltage, and when for high L is very much greater than IS, therefore we will get VOC is equal to this. And under illumination, the output electrical power P is equal to IV. Substitute the values I and V. The conditions for maximum power is dP by dV at V is equal to V maximum. So after substitute you will get 13, 14, 15, 16, 17 equations. This you can do it nicely. And the magnitude of Im is thus can be expressed from equations. So these are the equations we'll get Im and I in terms of Is, where we get the maximum power Pm is Im into Pa. So from 1920 we'll get from 19 minus 20 is simplified, you'll get the 21 equation, and if it's 21 further simplified, you'll get 22. So the maximum power gain is given Im. Substitute the values of Im and Vm. You'll get Vm in terms of the current. This is the equation we get, the 23rd equation. Then Em is equal to E, we will say final expression Em corresponds to the energy per photon delivered to the load at the maximum power point. And the ideal conversion efficiency of the solar cell eta is defined as the ratio of maximum power output to the incident power. So eta can be calculated. Then another quantity is called the fill factor, which is very important. To maximize output power, both short circuit current and open circuit voltage must be made as large as possible. For the most solar cells, the fill factor is about 0.7 to 0.9, which is an important figure of merit in its design. Thank you.